Alright, now we are going to start discussing automorphisms. And so you might remember from previous courses that a function from two groups, g to h, is a homomorphism if it's multiplicative. So that's a special term. Now, the special case when g is equal to h is called an endomorphism. I don't know if that's ever going to pop up much in this course, but it sometimes does, so it's worth pointing out. Endomorphism is a special type of homomorphism. It just means the domain and codomain are the same. On the other hand, if the function from g to h is a bijection and a homomorphism, then we know from modern algebra we have this notion of isomorphism. Well, in the same way, if g and h are actually the same set, we give this a special name. We call it an automorphism. So an automorphism is just an isomorphism where the domain and the codomain are actually the same group. So of course that means that phi of g times h is phi of g times phi of h, and phi is bijection. We're going to let aut of g be the set of automorphisms. Since every automorphism is a bijection, it follows that this is actually a subset of S of g, where S of g is the set of bijections from g to itself, also known as the symmetric group on g. And so the symmetric group on g is a group. This is a subset. The natural question is this subset a subgroup? And the answer is yes. The set of automorphisms is a subgroup. So the textbook actually just says the set of automorphisms forms a group, and then says the proof is left to the reader, and then points out that it's actually a subgroup. So the proof we're going to do is just by proving this fact, because if you're a subgroup, then you are in fact a group. And why would we want to do that? Well, because then we don't have to talk about associativity, because we can use the subgroup criterion to prove that we have a subgroup. So all I need to do is take sigma an automorphism, tau an automorphism, and then I just need to prove that sigma composed with tau inverse is also an automorphism. Which really means I just need to show this is a homomorphism. Why? Because, well, I mean, sigma and tau are already bijections, and so tau inverse is already bijection, and the composition of bijections is already a bijection. So we already know that this is an S of g. So we only need to show it's an aut of g, and the only difference between these two is that these are the ones that preserve the multiplication. So we just need to do a calculation. Let's consider little g and little h to be two elements of g, and I just need to show what happens when I apply this function to this product. Well, then I get sigma of tau inverse of g times h. And now I get kind of stuck. I'd like to say that this is multiplicative, but it looks like that's going to take a separate proof. So let's hold off on that for now. And you'll sometimes see this works, because this is the simplest version of the subgroup criterion, and sometimes it's useful. But sometimes you go through the proof and you see it doesn't, you get stuck, and when you do that, you go back and say, never mind, I'm going to do the longer version. So this is the simple version where all you do is write division. And we got stuck trying to do it, so now we're going to do the alternative version where I just get rid of the minus ones. Because now I know what I need to do. Tau is an automorphism, so it's multiplicative. So now I have sigma of a product. Sigma is multiplicative, so sigma of the product is the product of the sigmas. And now I get function composition. So at the very least, I managed to get the function composition to be an automorphism. Wasn't quite what we were looking for, but that's okay. Sometimes that happens. So then we just need to prove inverses then. So instead, we switched our objective and we decided to show closure under composition. Since we did that, we also have to show closure under inversion and the identity function. Well, what's the identity function? It sends G to G. That is a homomorphism. It is a bijection. It's in automorphism group. So the identity bijection is in here. So now we just need the remaining criterion, which is that we're closed under inversion in the automorphism group. The reason why one has to hesitate is because it's not necessarily clear whether or not these two are distinct or the same. But when you look at examples, you'll discover they are not. There is a group operation on endomorphisms where inversion is given by this operation, but that's not the operation we're talking about. We're talking about composition. So with respect to composition, this is actually not correct. So that's worth pointing out. So what do we do? Well, let's compute sigma inverse of G times H. We want to find a way to factor sigma inverse through the product. The only thing we know is that we can do that with sigma, so we need to find a way to introduce sigma into this equation so that we can use the fact that sigma is an automorphism. And so the way to do that would be to, well, there's two options. You'd either introduce it here as sigma inverse, or you'd introduce it on each factor. You think carefully and you try both, and you discover the appropriate approach would be this approach, or you introduce it on each factor separately. Then you use the fact that sigma is a homomorphism, to replace these two sigmas with one sigma. Then you see that you've got sigma inverse composed with sigma here, applied to sigma inverse G times sigma inverse H. But of course, sigma inverse composed with sigma is the identity function, and so you actually get sigma inverse G times sigma inverse H. So you do actually see that the inverse is also a homomorphism. So this is an interesting fact, and actually it's something you sometimes prove in modern algebra as a homework problem, given an isomorphism from G to H, the inverse bijection is also an isomorphism from H to G. And that's essentially what we just proved. Now let's come up with an example of an automorphism. Let's come up with a ridiculously general one. Let's suppose H is normal in G. Well then, this means that GH inverse is equal to H for every group element. In particular, fix your favorite G. Then what do we have here? We have a function called conjugation. And every time you conjugate by G, you end up with another H by G, you end up with another element in H because of this equality. In particular, conjugation lands back in H. And so one thing that's actually cool about conjugation is that it's actually an automorphism of the larger group G, but in this context we'll show it's an automorphism of H. I stated as phi of G, so let's stick with that. So it's an automorphism. Well, let's think about it. Is it a bijection? Well, these two sets have the same size, and you're defining a function from one to the other given by conjugation. You do send the identity to the identity. So, yeah, we'll go through the process, but why is it an automorphism? Well, let's check the conjugation property first, that it's a homomorphism. So first, if you act on a product of two elements of H, that's what you get. But if you secretly multiply by G inverse G in the middle, you will see that you get the product of the conjugates. Why would you do such a thing? Well, because we're trying to prove it's a homomorphism. So we do see that we do have a homomorphism here. So why is it injective? Now that we know it's a homomorphism, we can prove it's injective by looking at the kernel and proving that the kernel is trivial. That's one advantage of proving the homomorphism property first. So suppose we've got something in the kernel, then the function sends that element to the identity. So that means G times H times G inverse is the identity element. Well, you can solve for H by multiplying on the left on both sides by G inverse, and on the right on both sides by G, so that you can cancel out. And what do we get? We get that H is equal to G inverse times E times G. Oh look, it's just G inverse times G. It's the identity element. So the only element in the kernel is the identity. So the kernel is the identity, the trivial subgroup, and therefore phi of G is injective. And so we got that our map is multiplicative and injective, so all we need is surjectivity. Well, you need to take H and H, and we want to find an element that maps to it. So we're looking for a way to get an H prime, so that GH prime G inverse equals H. Again, the same trick should work. If you multiply both sides on the left by G inverse and both sides on the right by G, we've found the identity, the element of H we're looking for. Because we're closed under conjugation by every element of G, this is also true if you replace G with G inverse, so this thing on the right is in fact an element of H. So we can check phi of G inverse HG is in fact H. So we are surjective. So this is an automorphism. Of course, it's worth pointing out here that G is acting on H by conjugation. So we actually have a group action. And so based on our theory of group actions, we have a homomorphism from G into the symmetric group on H. And so this part about injectivity and surjectivity technically follows for free because that's what this action is. So the only thing we really need to focus on was the multiplicative part, but it was worth going through just to refresh our memory of how these proofs work anyhow. And the fact that it's multiplicative is the part that was interesting and new, because what that actually tells us is that phi of G, which is phi sub G, is actually in the automorphism group of H, because it's an automorphism. That's what we just showed. So actually, our permutation representation takes you into the automorphism group of H. So not only does conjugation by a given group element G give you an automorphism, the collection of all such automorphisms is a subgroup of the automorphism group of H. The textbook uses the word into aut H in part of their claims for proposition 13 in section 4.4. I would try to avoid that phrase because to me using the word into implies injectivity, but then they go on to describe the kernel of this map, and so it's not injective in general. So we've gotten pretty abstract pretty quickly. Given a normal subgroup H, given an element G, we constructed an automorphism. And then we also constructed a whole bunch of automorphisms. And in fact, we've constructed a homomorphism from the group G to the group of automorphisms of H. And so naturally, by the theory of group actions, this is actually a group homomorphism. And so one might ask, what is the kernel of this group homomorphism? Or equivalently, what's the kernel of the corresponding original action we started with? So we're looking for those G, where phi of G is the identity automorphism, which means those G were GH G inverse equals H for all H and H. So we're looking for those group elements for which this equality is true, which means we're looking for those group elements in the larger group G, such that G, little g here, commutes with little h for every element in the smaller group. That's just the centralizer. The definition of the centralizer of any subset was the elements in G that commute with every element of your subset. Of course, this tells you something about centralizers. It tells you that when H is a normal subgroup, the centralizer of H and G is also a normal subgroup. And then applying the first isomorphism theorem, we get one final fact, which is that G mod this centralizer subgroup is a subgroup isomorphic to a subgroup. Here, let's invent a notation for this. Odd H. So this is isomorphic to a subgroup. Since we often use the tilde for isomorphism, and we often use the less than or equal to sign for subgroup, this seems like a good shorthand for being isomorphic to a subgroup. And so we get a theorem that in the textbook is called Proposition 13, which was all the above facts that we've been talking about so far. That if you've got a normal subgroup H and G, then G acts on H by conjugation, and that this defines a homomorphism from G into the automorphism group of H with this kernel and then with this other fact. There are two corollaries, one where you let G be H. If you let G be H, what ends up happening in this whole theory, because certainly G is normal inside itself, then you get a homomorphism from G to aught G. In particular, this allows you to conclude that conjugation is a isomorphism. And so one fact that's worth pointing out that we might remember is if you have an isomorphism between two groups and you have a subgroup, like a subgroup in G, then that subgroup is isomorphic to its image in H. And so in particular, the corollary they want to claim is that when K is a subgroup of G, and G is an element of G, then K is actually isomorphic to its conjugate. Inverse goes on the right. Which you can prove directly if you really want to, but you get it for free from this more general theory. In particular, automorphisms given by conjugation have this feature that they send subgroups to subgroups, elements of the same order to elements of the same order. This is true in general for arbitrary automorphisms. These types of automorphisms are called inner automorphisms, by the way. The other fact we get from here is that the center in this case, the centralizer of G inside itself, is the center of G. So this tells you that G modulo the center is isomorphic to the subgroup of the automorphism group. And this isomorphism are exactly these homomorphisms. And these are called inner automorphisms. The other corollary is that the normalizer in G of a subgroup H modulo the centralizer of G of a subgroup H is isomorphic to a subgroup of the automorphism group of H. Why is this true? Well, because you're going to look at the normalizer of G of H acting on H by conjugation. And then you just apply the previous proposition.